In this video, I'm going to run through some basic titration calculations where titrations are just used to find concentration. So in a titration, you're going to have one standard solution. You'll know the concentration of that solution, and you titrate it against another solution whose concentration you don't know, and you can use the titration to find out that unknown concentration. I'm going to do this second example here. And first off, we're just going to highlight the information that we've got that's going to be relevant to our calculation. So I'm told I've got sodium hydrogen carbonate solution, and I'm told I have got sulfuric acid, and I can see that here in the equation below that these are the two things I'm titrating against each other. With the sodium hydrogen carbonate solution, I'm told the volume and I'm told the concentration. So centimetres cubed would be a unit for volume, moles per decimeters cubed, that's a concentration. So it's important when you're picking out the numbers that you know what the numbers actually mean. For the sulfuric acid, the concentration is unknown, that's what I'm trying to find, but I am told the volume 17.6 centimetres cubed. So this is what you'll be given in a titration question. They'll give you the volume and concentration of one solution, they'll give you only the volume of the second, and you're asked to work out the concentration of the second. So just to organise my information, I'm going to use my balanced equation and I'm going to write the information underneath. So sodium hydrogen carbonate is here, NaHCO3. The volume, as we said, was 25 centimetres cubed. The concentration is 0.1 moles per decimeters cubed. And then for H2SO4, the only information I have is that the volume is 17.6 centimetres cubed. To do the sum, I'm going to arrange this information in a table, which I have already filled out here. So I've taken the sodium hydrogen carbonate and the H2SO4, and down the side I've got volume, concentration, moles, and ratio. Before I inserted the volumes into the table, I converted from cm cubed to dm cubed by dividing by 1,000. So 25 divided by 1,000, 17.6 divided by 1,000. That's because my concentration is per decimeters cubed, so my volumes need to be 2. For NaHCO3, I was then able to fill in the concentration of NaHCO3. The ratio I got from my balanced chemical equation, so we can see here that the big number in front of NaHCO3 is 2, which means in my ratio I've got 2. There's no number in front of H2SO4, which makes the ratio just 1. And then to work this out, I'm using the following formula triangle. Moles is going to be concentration times volume. So all I needed to do was times these two numbers together, volume and concentration, to work out the number of moles. Then with my ratio, I saw the ratio is a 2:1 ratio, so I divided by 2 to work out the moles of H2SO4. And once I knew moles of H2SO4, I know moles, I know concentration. Sorry, I know moles, I know volume. Concentration is just moles divided by volume, and I was able to find this number here. So this is my final answer. This is the concentration of H2SO4. But if we look in the question, you're asked for that answer in grams per decimeters cubed. Now, when you work it out in the table, your concentration is always going to come out in moles per decimeters cubed because our volumes are in decimeters cubed, and we've also got moles. So if I want to go from moles to grams, all I need to do is multiply by formula mass. So the formula mass of H2SO4 is 98. I take the moles, I multiply by the formula mass, and that allows me to go from moles per decimeters cubed to grams per decimeters cubed. So that is your standard titration calculation, typically worth about 3 marks. The next example we're going to look at is slightly more difficult because they don't give you either concentration initially at the start of the, in the question. So if we have a look at what they do give you, again, if I look at my balanced equation, I can see what's reacting with what in this titration. So again, I've got sodium hydrogen carbonate, but this time I've got hydrochloric acid. If I look through the numbers, I'm told the number of grams of sodium hydrogen carbonate that is dissolved in 250 centimetres cubed of water. So they're telling me how I made up the standard solution. What they haven't told me is the actual concentration. I'm going to need to use that information. So I'm going to need to use these two numbers here to work out the concentration of NaHCO3. In the previous question, they just gave me that information straight up, but here I'm going to need to use that information to work it out. Once I know the concentration of my NaHCO3, they do tell me the volume, so I've been given the volume. So I have really been given volume and concentration of sodium hydrogen carbonate. And for the acid, I've just been given volume and I'm asked to work out the concentration. So similar to the last question, but just one extra step. We're going to actually have to work out the concentration of our standard solution first. So for the sodium hydrogen carbonate, we are told that we have got 2.10 grams, and we've made that up in 250 centimeters cubed. Now, before I can plug a concentration into my table, I need the unit to be moles per decimeters cubed. So I've got grams. The first thing I want to do is turn it into moles. And if I want to go from grams to moles, it's just going to be mass divided by formula mass using my G Mr. Moles triangle. The formula mass of NaHCO3 is 84. So my mass, the mass, as I said, is 2.10. That's in the question. Divide that by the formula mass is 84, and I end up with 0.025. So I've gone from mass to moles. However, I still don't have a concentration because this was the mass per 250 centimeters cubed. Therefore, this is the number of moles per 250 centimeters cubed. The units for concentration I need are moles per 1 decimeter cubed. A decimeter cubed is 1,000 centimeters cubed. So I know the number of moles in 250. I need to know the number of moles in 1,000. To go from 250 to 1,000, I would need to multiply by 4. So if I'm scaling up the volume by a factor of 4, I'll need to scale up the moles. So all I need to do is just take my value for moles, which is 0.025, and times that by 4. Once I do that, I end up with 0.1 moles, and that's the number of moles I would have per decimeter cubed. So that's the number of moles I have per 1,000 centimeters cubed, which is the number of moles I have per decimeters cubed. And that is a valid unit for concentration. So now I've worked out my concentration in moles per decimeters cubed. I already had the volume, so now I've got volume and concentration for sodium hydrogen carbonate, and I've got the volume for sulfuric acid. So just as before, I'm going to fill all of that information into my table. So before I fill in my volumes, I'm turning them into decimeters cubed. So these numbers are both given to me in the question. This is the value for concentration that I've just worked out. The ratio I'm getting from a balanced chemical equation. As you can see, there are no numbers in front of either, so I'm just writing down 1:1. I use volume times concentration to work out moles. The ratio is 1:1, so I'm going to have the same number of moles of HCl. And then to work out concentration, it's going to be moles divided by volume, and that gives me this number here. So if you're unsure of how to fill out that table, then just practice using the numbers for yourself. Make sure you can fill it all in. But this is the answer that I was trying to get. This is my concentration of HCl. Again, though, the question is asking us for the concentration in grams per decimeters cubed. In the table, it will always work out in moles per decimeters cubed. So to convert, I do the same as what I did before. I take the number of moles, I work out the formula mass of HCl, because that's what I've got the concentration for, and then grams is going to be moles times formula mass, and that gives it to me in grams per decimeters cubed. I'm just going to do one more. It's not different, it's just the equation makes it potentially look a little bit harder. So the two reactions above are your typical acid-base reactions. But you don't just use titrations for an acid and a base. You can also use them for redox reactions, as long as you know the volume and concentration of one solution and the volume of the other, and that there's a clear end point. You can use this titration technique to work out an unknown concentration. So here I have got, I've got iron 2 sulfate, and I'm titrating that against potassium manganate. Now, if we look at the equation that they've given us, And the question is saying iron 2 sulfate and potassium manganate. And then if you look down at the equation, it might be hard initially to pull out where those things are. Iron 2 sulfate is going to be FeSO4. The SO4 is not included in the equation because the SO4 is just a spectator ion. It's not involved in the reaction. But you'll see that the iron 2, so iron with a 2 plus charge, is here in the equation. It's right there. You're titrating against potassium manganate. Okay, so potassium we know obviously is the symbol K. If you look down at your equation, you're not seeing K. But again, that's because K is just a spectator ion. It's not involved in the reaction, so it hasn't been included in the equation. Manganate is MnO4, so from manganese, and then 8 implies oxygen, so it's manganese with oxygen. And again, I can see that here in my equation. So these are the two things that I'm iterating against each other. They mention that you're using, that it's acidified, which is why I've also got H+. I'm not going to be using that in my calculation. I'm just focused on the manganate and on the iron. Once we pick that out, essentially it's just exactly the same as before. I'm told I've got 25 centimetres cubed of the iron 2 sulfate, so I'm given the volume, so I'm going to write that in there. I'm given the volume. And I'm also told the concentration of the iron sulfate, so 0.100 moles per decimeters cubed. The concentration is in the right unit straight away. And then I titrated with potassium manganate, and it required 20.6, so 20.6 centimetres cubed. So just as before, I'm given volume and concentration of one solution, I'm given volume of the other, and I'm asked to work out the concentration of this potassium manganate, and I'm asked in moles per decimeters cubed. So once I've got that information pulled out of the question, it's exactly the same it was before. I'm drawing up my little table. I'm converting my volumes from cm cubed to dm cubed before I insert them into my table. So I'm dividing by 1,000. That concentration goes straight into my table. To work out moles, it's volume times concentration, so I get this value here. The ratio is 5:1. I've got a big 5 in front of the Fe. I've got nothing in front of MnO4. So once I know this number, I divide by 5 to find this number. And once I know moles, it's going to be moles divided by volume equals concentration. That value for concentration comes out in moles per decimeters cubed from my table, and that is what I'm asked for in the question, so no further calculation is needed. When you're doing these questions, please use the table. It makes it really easy to follow your work. If you make a mistake, the examiner will be able to see where that mistake was made and give you error carry forward marks. If you've just got numbers all over the place or you don't have any workings at all, you make one mistake, you will lose all 3 marks. So please make sure that you're presenting your work in a clear and logical format.